Hey folks, I'm Danielle, and I'm a staff engineer at VMware, working on Kubernetes things. Before VMware, I worked at HashiCorp on Nomad, which is their cluster orchestrator. You can find me on Twitter at Endocrimes, and in this talk, I'm going to be giving a very short refresher on the basics of Byzantine fault tolerance and Raft. And then we're going to switch over to the terminal to take a simple key value single node service and distribute it using HashiCorp's Raft library. Raft is a consensus protocol, and I'll be talking a lot about consensus for the next few minutes, but what does that actually mean? Well, when you have a service running on a single node, consensus isn't really much of a problem. You receive a request, you can update your state, and if there's multiple clients, then you can serialize those requests and maintain some level of consistency fairly easily. However, we don't tend to run single instances of our stateful systems because computers are bad and can break for a multitude of reasons at any given time with little to no warning. So, how do we make something like this run across multiple systems? Well, we need to get multiple servers to agree with each other while handling failures in any of those nodes. This problem was originally stated by Leslie Lamport and friends in a 1982 paper called The Byzantine Generals Problem. They tried to abstract away the technical problems of consensus and present it in a way that anyone can understand. So, to paraphrase their work, imagine a city and some generals plotting to take it over. They need to coordinate multiple battalions to surround and attack the city at the same time. Otherwise, they'd lose the battle and they'd fail to take the city. Communicating only by messenger, the generals must agree upon a battle plan, but one or more of them may be traitors who will try to confuse the others. The problem is to find an algorithm to ensure that the loyal generals will reach agreement. In the paper, it shows that using only oral messages, the problem can be solvable if and only if more than 2/3 of the generals are loyal. So a single traitor can't ruin it for everybody. This led to the definition of Byzantine faults, which are a class of failures that belong to the Byzantine generals problems. They're some of the most difficult and unpredictable failure modes to deal with in distributed systems, because they're faults where components may fail and there is imperfect information on whether a component has failed or not. This can be really interesting, and it's worth doing more reading about if you're interested in the foundations of distributed systems. This eventually led to Lamport also discovering Paxos, where in the paper he describes a parliament on the Greek island of Paxos after being nerd-sniped by Liskov and Lynch in a 1980s paper that said consensus could be solved, and then spending years trying to prove them wrong. And when he proved them right and invented Paxos, it took him 10 years to publish the paper because, well, it was Greek to many engineers. But as my coworker told me recently, not to Greeks because of the anglicization of words. He then published Paxos Made Simple, but most people still don't understand it well enough to implement it safely. And, well, Paxos is super interesting, but I'm gonna kind of skip over the details here because that could be an hour-long talk in itself. So it feels like I kind of just went off on a tangent, because how is this relevant to Raft? Well, Raft is a consensus protocol that was designed to be understandable and is based on Paxos. It's gained a lot of popularity in modern distributed systems despite being a fairly recent development. And this is based a lot in the fact that from the outset, it tried to make building production-ready distributed systems easy, and it helps that it has an adorable little mascot. So, how does Raft work? Well, in the beginning, there is no leader. And as the nodes start up and try to join the cluster, each node is assigned a random timeout. And they're counting down and they're waiting for something to happen. Because when the first node reaches the end of its timeout, it will start an election and enter candidate status. And in Raft, we have 3 different states that nodes can be in. The follower, which is where most of our servers are, the candidate who is trying to be the leader, and the actual leader. Because Raft is divided into terms, and there's one leader per term, or there is no leader. No leader cases happen for a variety of reasons, such as an election failing, due to conflict, out-of-date Raft logs, or there not being enough nodes left to reach a consensus. But I'm going to skip over the details of those here. So our friendly little node comes along and asks everyone, hey, please vote for me, I'm going to go do the things. And there are 3 end goals we can have during this election. Either the initiator wins the election and becomes the new leader, someone else wins the election and becomes the leader, or nobody becomes the leader because we can't reach consensus and we retry until we can. The elected leader will continually heartbeat the other nodes. There's a timer, and every period of usually a few seconds, the leader sends a heartbeat, and assuming there's a successful response, it resets the timer and keeps going. But if you're a follower and you haven't heard from the leader for a while, and your timeout expires, then you can become a candidate and start a new election process. In this case, an election will happen and you might become the leader, someone else might, or nobody will and you'll try again. This usually happens if a node is disconnected from the network, the leader goes down, many reasons. So that's pretty cool, but, well, how does this help me build a distributed system? Well, it turns out the relatively simple thing of, am I or am I not the leader, is really useful primitive for building consistent, partition-tolerant distributed systems. Especially when you apply this to replicating logs, which is where the Raft mascot comes from. Replicated logs let you rebuild and distribute your application state across many nodes, and although the leader is the one that ultimately makes decisions about where work happens and what state can be written to the log, you can also parallelize some of that work with optimistic concurrency. And usually followers can also serve GET requests and the like. But optimistic concurrency is a much more complicated topic. So I just said a lot of words, but you can't really take those and go build a thing using Raft, so let's fix that and do something a little bit more practical. So we have a small key value store that reads and writes to an in-memory map with a HTTP API. And right now, it only runs on a single node. So let's take a look at the code now. So now let's take a look at our simple key value application and take a look at where we're starting from before we try and, distribute it. So I have it running here already. And if we try and get a key, we see we get nothing back. And if we write a key, we can then retrieve it. And, everything is fairly simple, but it works. So let's shut that down. And actually look what happens when we make a request to it. So we have 2 packages. We have the HTTP package, where we have an API server, and then we also have a store package, which is our data store, and where some of our other code is going to live later. So if we open up the server, a server takes a configuration that has a bind address, a store, and a logger. And when we start the server, we set up some basic timeouts, listen on the address, and handle it. And when we get a request, it comes through the serve HTTP function. This creates a random request ID just for keeping logs together. And if the string has the prefix of kv, we end up in the handle kv request function where we grab the key we're trying to get. If there's no key, then we return an error. Otherwise, we end up in here where we either are getting something and therefore we ask the store for the key. If there's an error, we return it. Otherwise, we return the response. And when we put, we decode the request. And if there's an error with that, return it. Otherwise, we try setting on the store. And if it's a delete, then we set an empty string to remove it. So when we have our GET request, we end up in here, and we try and get from the store. Which, oops. As we can see here in the interface for the store, it gets the value for a given key, and the value will be empty if the key could not be found. And the same is true for setting. Sets updates the value for a given key, and it's removed if the value is empty. The store is pretty simple. Ignore this for now. But we have data, which is a map, and then we have a lock for the map. And when we get something, we take the lock, defer the unlock, and get the data. And when we set, we take the writing lock, we defer the unlock, we check to see if the value is empty, then we delete the data, or we set the new value if it's not empty. Cool. So now we've seen like our basic little server. Here at the entry point, we get the bind address, set up the store, create the server, and just run the server until it ends. But let's see what that's actually going to take to sort of like develop a little bit further. So, as we just saw, we have a fairly simple application that just about works, but let's say for some reason we now want to run our application in multiple availability zones because a new application depends on it that needs higher availability. Or we also want automatic failover between those nodes to, keep everything running smoothly. So with the magic of here's one I made earlier, let's take a look at the changes and how you can do this at home. Now we have a little bit of a demo. So as you can see here, we have 3 different nodes in our Raft cluster. This node started here and immediately became the initial leader. And here you can see we have 2 followers, and not much is currently going on. If we try to get a I did the wrong pot. So if we try getting a key, you can see there's nothing set. But if we write something to the leader, that is not the leader. Oh, 31,000. That writes successfully, and then we can get that back from any of the nodes because it already transferred over, which is pretty great. So how did we get to the point where we had something that was replicating across multiple nodes, with Raft? Well, if we switch over to a different tab, what did we change? Well, our initialization got a little bit more complicated because we need a few more things now. So what we added was an address for Raft to communicate through, the ID of the node to identify the server within Raft, a join address to identify a server that we should join to form a cluster with, and whether we are bootstrapping a new cluster. And the bootstrap flag basically means that when you start up, you should immediately become the leader, and as new nodes join, you can sort of renegotiate that. But that kicks off the initial process with the HashiCorp Raft library. In HashiCorp projects, they also make you specify the number of nodes to expect before starting the leader election process, which can help avoid having any split brain or like similar problems in production environments. But with some manual starting of the initial cluster, then you also don't really need to worry about that. So when we start the server, the first thing we do is we pass the flags, we set up logging, and we create a store. Now we also pass in the Raft bind address because the store is where it's going to have like Raft be managed. And we added this open step. So what this step does is it sets up some Raft configuration. Then, because Raft has a pluggable transport protocol, it sets up a new TCP transit protocol with the address that we specified, with a couple of like timeouts and stuff. Then we create some storage for both like the incoming logs and the stable state, and we create a new instance of the Raft library. If we're bootstrapping the cluster, then we also initialize some configuration to ensure that the current server is a member of that cluster before telling it to bootstrap the cluster. Yeah, so then if we jump back over to main, after we start the cluster, if we are joining an existing cluster, we create a new client and request to join that cluster before setting up our own HTTP server and starting the application. And so the way we actually join nodes together, as you can see a little bit here, but I'll start that again now. As you can see, the leader's a little bit sad that everybody else went away, but if we go ahead and clear these and make you a little bit bigger, when you're starting a node, we give it a node ID, and in the first case, we bootstrap the node. And as you can see, the heartbeat timeout already sort of expires, and it enters candidate status and elects itself as the leader. Then when we add the first node, we tell it to join the initial one. We give it its own unique Raft address and HTTP address. And as you can see here, the node successfully joins. And any existing logs get sent to that node. And when we add the final node, the same thing would happen again. Which is really quite useful. So if we jump back over to the code, we've seen now how to sort of like bootstrap the Raft cluster itself. But what changed in sort of our data path? Well, internal package store Our get implementation didn't really change. We still return the data from the map, but the interesting part is where we update our state. So previously, we took the log and directly updated our data, which is fine when you have a single machine, but here we need a little bit of consensus, because we need to make sure the state gets applied on the majority of machines and will eventually make it everywhere. So what we do now is we ensure that Raft was initialized, make sure that we're the current leader, and then we create a new Raft message. The Raft message basically says set some key to some value, and we encode it in a way that can be sent across the wire. And then we call this funny Raft apply function, which gives us a future, and that future will say to us whether the message could be applied successfully or if there was a problem. This apply function will go ahead and make sure that a majority of nodes receive the request and accept it before committing it and saying there was no error with the request. So this ends up inside our finite state machine functions. Specifically, this function will be called on every node. This is the apply function, which takes a Raft log entry and applies it to its state. So we can support arbitrary different numbers of message types, but right now we only have one, the update KV request type, which calls this function, and we take the lock, pass the message, and then we apply the state to our map, exactly the same way we did before. And because this is Raft, it's almost impossible for us to lose any sort of operations that make it to the log. And so even if a function is non-communicative, everything will always be applied in the same order, which means there's just a whole order of data consistency problems that you kind of don't really need to worry about too much, which is really great. The only thing you want to be careful of is to not make use of anything like time or similar things in your state, because then different servers will end up with different state. And that's a sad time. But this basic primitive is how most Raft-based systems are built. So that includes things like etcd or console or nomad, cockroachdb. They all fundamentally somewhere have a finite state machine that is applying entries from a log to some other internal state. In HashiCorp's products, that's usually BoltDB. I think etcd now uses a fork of BoltDB. Some things will then apply that to a MySQL database or SQLite or whatever else. Yeah. So you might now be thinking that these logs must get pretty big if every write goes through them. And well, yeah, but Raft kind of has a solution to that in the form of snapshots. So a Raft snapshot takes the state of the, takes the rendered state at a given point in time, and then compresses, removes the logs before that point, and the log entries become only, from that current index. Which means if you want to restore your state, you can load a snapshot and then replay any logs that were not in the snapshot, and you can truncate the, old logs. This doesn't really matter in a tiny application like this, but it is a required part of implementing the interface. And yeah, so you have to implement a snapshot function where we take a read lock, we copy the data, put it into a struct that conforms to an interface, and we also let you restore from an old snapshot. That interface is fairly simple. You have to sort of write the data to an arbitrary sink because you might be storing it in memory, but you might also be flushing it to disk or anywhere really. But yeah, that is the sort of minimum viable thing you need to set up an application with HashiCorp's Raft library. Now that we have a better understanding of how to use Raft, and with the HashiCorp Raft implementation, if we wanted to take that and start making it, more production ready, where would we go? Well, something that many people would want to do is start forwarding write requests to the followers to the leader. This is really useful if, say, your application is behind a load balancer, or if you don't want to worry about who the leader is right now. This is something that's common in a lot of Raft implementations, such as in all of HashiCorp's products. And you may also want to add persistent storage with BoltDB, because although right now, when a node starts up and doesn't have any state, it can download that from another server. If you have a lot of state, that can quickly become quite slow. It's much nicer to only have to transfer deltas. And it's also nice to add APIs that control cluster membership and let you export metrics about who's the leader and leader elections and stuff like that. And also, by exposing the Raft index in your API, you can do really powerful things with clients, like saying, I wrote this thing at Raft index X, and when I want to get at least Raft index X, so I can guarantee read after write consistency, which is really useful. So, thanks. As I said before, I'm on Twitter at endocrimes, and you can email me at danny@builds.terrible@systems if I forgot to post the slides or code or anything else. I hope you all enjoy the conference.